One more. Do a brief introduction. I don't. Test. Test. Okay, can anybody on the call confirm that you can hear us?
Yes, we hear you well.
Okay, great. We're going to go ahead and get started. Welcome to the third and final for the semester FOCI Gen AI / LLM users group talk. I apologize that we're starting a little late, and also that there was a 2.5-month gap between these. John Erickson was going to present in April, but his presentation was scheduled the same week as the quantum unveiling stuff, and we thought maybe we should move that to a later date. So John is going to present at one of these talks. We don't know when yet, but he'll talk about LLMs and copyright law. But for now, we have Abraham returning from, he gave the final talk last semester. And today he'll be talking about something much closer to exactly what his PhD is on, which is LLMs for audio applications. And I will let him take it away.
All right, thanks, Aaron. Welcome to this talk. I apologize, we're getting started a little late, and just a fair warning, we might end a little late as a result. So when 6 o'clock rolls around, if anybody has to leave, or sort of 7 o'clock rolls around, if anybody has to leave, definitely understandable. The talk will be recorded, so you can catch whatever you miss on the flip side. All right, so let's get into it. LLMs for audio applications. Can everyone on the call see the slides advancing?
Yes.
Okay, great. So just to start, right? LLMs are usually discussed in the context of natural language, right? And natural language in humans is actually first acquired in the audio modality beginning in infancy. Children will be typically fluent at communicating with natural language years before they read or write their first word of text. Contrast that with LLMs that are pure, or mostly pure text, and learn language purely in that form. So the question is, can large language models learn to model language without actually using text? Can they directly understand and generate audio? And that's what we're going to explore in the rest of this presentation. Additionally, some extra motivation here is that audio, in general, audio applications enable more natural interaction between humans and computers by interacting through speech. Applications that you're probably familiar with include digital assistants like Alexa, accessibility aids for people who can't see the screen, customer service automation, like routing calls, stuff like that, transcription and translation, more engaging chat agents, and a little bit sort of for fun, smart NPCs and video games in immersive worlds. And on that topic, let's kick this off with having a little fun. Let's take a look at a smart NPC concept that showed up around the beginning of, I think it was like mid-2023.
We live in a slave world called the Matrix. The humans have been bound and kept in a state of slavery and ignorance. We can free ourselves from this system. We must rise up against the Matrix. Please, listen to me. You're living in a simulated world.
Yeah, I know. It sure doesn't feel real sometimes.
Let me show you the truth.
Not sure I want to know the truth. Seems like it's better to just stay in the dark.
No, it's different. So that, a concept of how spoken dialogue systems based on language models. In that case, I think they're using ChatGPT in the middle, can help make video games more immersive. So just some quick background on language modeling. I think at this point, if you've attended the previous FOCI talks, this will probably be a review, but just in case, language models are doing next token prediction. So we feed language in tokens, and we predict the next one. We call that autoregressive generation. And examples of models that do this are GPTs 2 through 4, llamas 1 through 3, Mixtral, etc. So if you're familiar with any of those models, then that's what they're doing. They take in these tokens, they embed them. There's some attention mechanism that attends over the context, and then it predicts the next token. Words are tokenized into small units that might be actually smaller than words. They call it subword tokenization. And the subwords are mapped using a vocabulary to a set of discrete integers. These integers are then used to look up an embedding from an embedding table. And the embedding is a vector that numerically represents the meaning of the word. And it's that vector that's actually fed into the LLM. We don't feed text directly into LLMs, we feed these vectors. So that's really all the context we need to talk about audio tokenization, which is where we're going to start on our journey of looking at audio applications in LLMs. So the immediate question here is, when we build an audio language model, what are the tokens going to be? So acoustic tokens, they need to represent units of sound instead of units of language. So we can't use words, right? Words don't necessarily exist in the same form in audio as they do in text. So for this, we'll turn to an audio codec. And if you've ever heard of MP3, AAC, FLAC, and WAVE, which, if you ever stream music to your phone, you're probably using one of these. These are codecs. They take audio, they encode them into a discrete digital signal of highly compressed bits, or in this case, integer integer values, and then a decoder on the other end will take this discrete signal and reconstruct it into audio. So this is what's streamed over the internet, is actually this intermediate compressed format, and you have a codec on your phone, which is then taking that and translating it back into raw audio that's sent out through your headphones. So these discrete units can actually be our tokens for language modeling of audio. Except we don't want to use the same types of codecs that are used for streaming music, because these have a pretty high bit rate. In contrast to MP3 and AAC, which typically go between 96 and 320 kilobytes per second, neural audio codecs, so codecs implemented using neural networks, can achieve between 1.5 to 24 kilobytes per second. And this is important because if you think about it, the amount of tokens that we have translates to the bit rate, and then also the amount of tokens we have translates to the context length. And if we have our bit rate is too high, our context length is going to be too high. So that's why we use neural audio codecs. Yes.
Quick question. In that amount of the kilobytes, it's still audible for us? We can still understand what's going on?
Yes, because the decoder is intelligent enough to decode very, very, very compressed representations back up to audio. So a neural audio codec, for example, is going to take audio sampled, let's say 24 kilohertz, which means 24 samples per second, or 24,000 samples per second. And it's going to produce vectors out of an encoder that the vector is going to represent a small frame of the raw audio sample. And it produces these vectors at a much lower frame rate, let's say 75 vectors per second. And if we feed these vectors back to the encoder can reconstruct the sequence back into raw audio waveform. But this is really, if you think about it, a lot more information than the raw audio waveform itself, because the raw audio waveform itself is just a single continuous floating point value, whereas here we have entire vectors, maybe of size 1024 or 2048. So to compress this, we need vector quantization. So vector quantization will take the vector space of audio encodings and break it up into discrete regions. And this is pretty much k-means. So we do k-means or some equivalent algorithm that separates and partitions the space. And we get the centroids of the partitions in this audio encoding vector space. And we can take those centroids and index them and put the centroid vector values into an embedding matrix, or what we call a code book. The embeddings, instead of calling them word embeddings, we call them code words. And instead of calling it a word embedding matrix, we call it a code book. But it's the same concept. We replace the vectors with this discrete sequence of integer values, which point to these centroids in our audio encoding embedding space. And now we have a very highly compressed sequence of code word indices that the decoder can actually restore back into an approximate representation of our original encoding vectors. So the decoder is then able to take those approximate encoding vector representations and convert them back to reconstructed audio. So some text NLP analogies, which I think I just already went over, but I'll go over them again. A code word index is basically a token ID. A code word is a token embedding, and a code book is a token embedding matrix. So it's the same exact idea, just applied to, it's just that the tokens themselves are somewhat arbitrary compared to language where they have some human readable meaning. Yes?
So in this shape, though, the size of the embedding that responds or corresponds to each token is still the same before and after this k-means-based computation.
Yes.
So what's like the benefit? Because then you're losing a lot of information by doing it.
Because if you don't do that, then you're going to have to transmit the original stream of vectors over the network, or in the case of an LLM, you would have to. You couldn't do probabilistic language or autoregressive language modeling with a sequence of vectors. You have to have discrete tokens to generate the probability distribution.
I see. So for the k-means, the plus centroids are predetermined between two parties, and then they can each send the indices.
Yes. Yeah. I should repeat the question for the people on WebEx. The question was, what's the benefit of doing the quantization here versus using the original vectors, because you would lose information. And that was the answer, was just that language modeling requires a set of discrete tokens in order to generate a probability distribution over the next token. And also, even if we weren't doing language modeling, the sequence of original vectors would be a much higher quantity of information than just the sequence of indices. So moving forward, we know that the reconstruction of the vectors from their quantized form can be lossy. So what we do is use residual vector quantization. Residual vector quantization is a pretty simple concept with a very fancy name. The concept is we subtract the approximated vector from its original, and we get a residual, or an error vector. And we can actually create another vector quantization layer with using those residual vectors rather than the original encoder vectors. So we can compute first the original encoder vectors, quantize them, restore them to their approximations, get the residuals, and then we can repeat that. We can take the residuals, we can quantize those, approximate them back, and then sum their approximations together to get a more accurate representation of the original encoder vector. And you might ask, well, wouldn't the residual approximations have their own reconstruction error, right? Well, you can do this again. You can do multi-level residual vector quantization. I don't know, it sounds even fancier. So eventually you can have many levels of a residual vector quantizer, each level quantizing the error from the level below it. And when you sum together all the approximations, you get a more and more accurate representation of your original encoder vector. So using this framework, we now have a powerful general neural audio codec, which we can use to discretely represent audio. And 3 examples of these are encodec, soundstream, and fun codec. If I remember correctly, encodec comes from Meta, soundstream came from Google, and fun codec came from Alibaba. There are a couple other codecs which I'm aware of, which I don't have the space to fit in the slide. So, but essentially, if you look at the diagrams, the architectures of these models are very similar. They have an encoder, which is squeezing the raw audio down to its to a vector representation. They have the quantizer, which is the residual vector quantizer, which does the discrete representation, and the decoder, which then expands the vectors back to the audio waveform. And by the way, vector quantization is not just for audio. You can use it anywhere that there's a vector space. So if you have a vector space of images, then you can get a sequence of tokens, which can then be used to reconstruct images. And this was done in 2017 in the VQ-VAE paper, which used a vector quantized VAE, or variational autoencoder, to do image generation. And it actually turned out to become a major part of the DALL-E series of image generators. So all that stuff being covered, we can go on to audio language modeling. So now that we can tokenize the vocabulary or the audio into a discrete vocabulary, we can proceed pretty much exactly like we do with text language modeling. We feed in audio to an encoder, we get our audio tokens out, we predict the next ones, take those next ones and feed them into the decoder and get the audio continuation. The concept's that simple. But there are some practical challenges with this. The first one is the increased sequence length that comes in the audio modality. For example, with encodec, you have 75 tokens per second, per codebook. So if you model, let's say, 2 codebooks, you would have 150 tokens per second. And if you think about it, people only speak maybe 2 to 5 words per second. So in text, that would be about 10 tokens. In encodec, that's about 150 tokens. So we're orders of magnitude higher sequence lengths. And the second challenge is dealing with the multi-level RVQ, the residual vector quantizer. And in this example here, we now show what this would actually look like if we have 4 codebooks. So we would have to decode all 4 of these code books before we could feed it back into the audio decoder, not just the one. And this is a real pain. And the reason why it's a real pain is because there's no unified way to handle it, and it's a non-standard way of doing language modeling. So one way is to predict multiple tokens per time step. So just like here, every time step we don't predict 1 token, we predict 4. But the issue there is that it's a non-standard decoding implementation. It's not compatible with most of the LLM ecosystem, including inference servers and optimized LLM implementations. It also has poor compatibility with existing sampling methods, mainly because there is a causal bias between these levels, right? The token you predict at the lowest level will influence which token you predict at the next level. And if you're predicting them all in parallel, then how do you do sampling? You might sample a residual vector token or residual token, which has nothing to do with the first token that you sample. So the other option is to flatten the codebook and stretch each time step into n, for example, 4 for a 4-level RVQ tokens. So the issue there is that it exacerbates the issue number 1, right? So if you, just like I said, if you have 2 code books and you flatten them, encodec would go from 75 to 150 tokens per second. If you have 4 code books, you're talking about 300 tokens per second. It just gets worse. That leads to slower inference, slower training time, and worse conversions, and it requires more GPU memory. So yeah, it's a pain. And this was formalized, sort of the challenge and some solutions to it were formalized in this paper, which we'll come back to a little bit later, which summarize those things, those two approaches we just talked about, in addition to two other approaches, into what they call codebook interleaving patterns. So the first one over here, if you look at the top left, the flattening pattern is where each time step you basically model the next token, even if it comes from another codebook. So you would do for time step 1, you would do codebook 1, codebook 2, codebook 3, codebook 4. Time step 2, codebook 1, codebook 2, codebook 3, codebook 4. And then you've actually done 8 time steps, not just 2. So there's also the parallel pattern, which is the other one we discussed on the last slide. There's the course first pattern, which is a hybrid approach where the first level is done autoregressively, and then the second level is done in parallel, or second to nth level is done in parallel. And then there is the delay pattern. The delay pattern basically combines the flattening and parallel patterns, where tokens are predicted in parallel, except you predict not the current time step for the residuals, but the previous time step. So it solves the issue of losing causal bias between levels. So I'll come back to this if there are questions, but and I know this can be a confusing part of audio language modeling, but we have a lot of slides to get through, so I'm going to move forward. But definitely note if you want to know more about this. I'm happy to have a conversation afterwards about like the intricacies of dealing with this. So here are some early examples of audio language models from 2021 through early 2023. And this was just last year, so we call it early examples because this field is really nascent. It's just now starting to yield fruit. So in 2021, there was a paper called on generative spoken language modeling from raw audio, or GSLM. And here what they did was they took an encoder, a decoder, and what they call a ULM, or a unit language model, which is essentially the exact same type of language model we talked about in the last couple of slides. This was one of the first papers in the space, so they didn't really have a standardized terminology for all these things, so they made up their own. But it's basically the same thing. You have the encoder, you have vector quantization over here using k-means on MFCC vectors. MFCC is like a way to encode features of audio, and then does the language model, and then it converts that back using a custom decoder. The decoder, the ULM here, was basically using the same architecture of GPT-3. So nothing special. And to decode the audio on the other end, they used a modified version of Tacotron 2, which, if you remember from 2018, was a state-of-the-art text-to-speech model. Except instead of feeding text into the model, they fed code words into it. And instead of using text embeddings, they used the code words out of the residual vector quantizer. So let's listen to some samples from the earliest known audio language model. I guess we can go with the one that says best, right?
But now we shall be there, they said. Then I will go into the lion to pay the price for them. They went on as well as many other best people. They went into the big back room where we were, they said.
So the language that was generated doesn't really mean anything. It's not coherent, but it sounds like language, right? There's also some conditional examples where it starts with a prompt and then tries to continue it.
Cried one of the women. He took no notice of her.
This was from an audiobook recording. So that's the prompt, and now it tries to continue the prompt.
Cried one of the women. He took no notice of her. He looked up and saw that it was a great pity. He saw the baby who was being called.
Oh, pretty cool, right? there's more demos here, but we're not going to go through them. There's plenty of more demos to go on other models. Then we come to Audio LM, which came out the following year. This was from Google. Audio LM has a 3-stage generation process. So first, it feeds in the audio, and it uses a semantic codec. So when I say semantic codec, I mean that it is not for the purpose of encoding and then decoding the audio. It's just for the purpose of encoding the audio into units that carry semantic meaning. The semantic codes are fed into a decoder-only autoregressive language model, which then generates a continuation. All of this is then fed into an acoustic model, which uses a traditional neural audio codec, like I think it's SoundStream that they use, which translates the sequence of semantic codes into acoustic codes. And then there's a third stage, which does coarse to fine generation. So it takes the sequence of coarse grained, which means the first 2 levels of the residual vector quantizer, and it predicts the 3rd through 8th level of the residual vector quantizer to get a more fine or high quality audio output. So it's a pretty significant step in the direction, because they don't just support tech, they don't just support speech, but they also support music generation. And we can look at some examples from this. So here's some speech examples. So here's a 3-second prompt, which will then be continued.
This transient spring and lighting up our...
And then here's the continuation.
This transit spring and lighting up our dreams by its brilliancy and beauty, a power which, if we shut our eyes to it, will not shut.
I have a question about that.
Yes.
Does the continuation, do they like force the prompt at the start, or would that prompt, like the very first 2 seconds of that continuation, I mean exactly like the prompt, was that generated by and part of the continuation, or did they create in?
Yeah, all they did was they took, or sorry, the question for the people on the phone, was all of that, or was the, I guess the question is, was the prompt injected in the beginning of the context and then it just continued it, or was it, I'm not sure what I understood what the second part of the question was.
Well, I guess to me, the first 3 seconds of the continuation sound like were the same as the prompt.
Like they regenerate the prompts as they try to.
Oh, okay, yes, yeah. They repeat the prompt so that you can hear it seamlessly move into the continuation. Yeah, okay. Here is an example of speech that has sort of acoustic effects in the background.
I shall like to see her. She must be an. I shall like to see her. She must be an angel among men, but she will soon be found out. She will go into society, and she will take.
Now notice that the model not only continues the speech, but also preserves the background conditions. The context window, the question was, what's the context window for this model? If I remember correctly, it's no longer than 2048. It might have even been 1024. Not that many, maybe, yeah, 10 or less. None of the samples they have are more than 10 seconds. We can also see some music generation. So here's the prompt. And here is the continuation.
It's memorization from Beethoven. I don't think, yeah.
So the model is doing the speech and the piano continuation in the same way. It's just generating those acoustic tokens and autoregressively. Yes.
What about the third column, the audio?
Which one? The acoustic only. Okay, so that one is where they take out the semantic tokens and they just do modeling with the acoustic tokens. So they don't use the semantic tokens came from a model similar to Hubert. I believe it was called Wave to Vec BERT, which was a proprietary Google model which was never released. And SoundStream is the actual neural audio codec. So here they don't use the Wave to Vec BERT semantic tokens. They just use the acoustic model. Yes. I'll go into them once I get back to the slides a little bit in more depth. Yes.
Yeah, no, I was just gonna say, just wanted to say that that's always my favorite. So random, so interesting, which is one of the things that LLMs do well sometimes in creative. That one.
Yeah. It's interesting perspective. Yeah.
I think
yes.
probably they look very similar in terms of the product. That's the essential difference between them. Besides the event that they created. Or
So,
just me that didn't hear any difference.
You didn't hear any difference between them?
Not it's true. I think the sound, no, it's not the same. No, but sound will be created from the same stuff.
Yeah. So the sound, it sounds the same, but the difference that to be aware of is that the sample that used the semantic tokens was a lot more coherent. It preserved some repeating structure over time, whereas the one which was acoustic only was more random, which Elkin said that he liked. So this actually gets into the very nature of the difference between semantic and acoustic tokens. Well, I'll take your question first. Okay. The frame rate for semantic tokens is lower than that for acoustic tokens. I forget the exact numbers, but it's definitely lower. So the difference here is that the semantic tokens are more coarse-grained. So like I was just saying, there's a lower frame rate. There's fewer semantic tokens corresponding to a second of audio than acoustic tokens. The semantic audio tokens are meant to capture the meaning of the unit of audio. Like, what is it that is actually going on in the audio versus capturing the details of the sound. The acoustic tokens, on the other hand, aren't concerned with the meaning and are more concerned with reconstruction of the sound. And a good example of the difference would be acoustic tokens would capture voice reconstruction. So to keep the speaker's voice consistent over the course of a speech. But the semantic tokens would be more concerned with what the speaker is saying. So if you just use the semantic tokens, you wouldn't be able to get a consistent voice. And if you just use the acoustic tokens, you wouldn't be able to get consistent language. Yes?
When I'm thinking of semantic modeling, I'm thinking about Mars. This is
not even going there. Yeah.
So, Abraham, that was just came about. So can you please compare in more detail what is a semantic token? I don't know what to.
So, I guess let me try to explain it a different way. The question, by the way, over the phone, if you can hear, was what is a semantic token? Let me think. So, I guess the semantic token is what you're saying, and the acoustic token is how you're saying it. Hopefully it's a more concise explanation and more clear. All right. Yes, go ahead.
So maybe it's a diagram, but it looks like the semantic tokens come first, and then like one semantic token refers to like 4 audio tokens. How do like for it to be an autoregressive model, should they be like interchanging order for audio tokens? Like how can they do like auto outside of their?
Good question. The question was how can we do autoregressive language when we have, or sorry, autoregressive language modeling when we have different rates, token rates between the semantic and the acoustic tokens? And the answer is that it's actually done in a 3-model cascaded fashion. So first, the semantic model is run. It's a separate transformer. It runs to generate these future semantic tokens. The second one is another separate transformer, which translates the full sequence of future semantic tokens into a full sequence of coarse acoustic tokens. The third one is a separate transformer again, which then generates the remaining codebooks. So it doesn't have to interleave them. It does all of one, then all of the other, then all of the other.
So this is like to generate the next window line overlap.
Exactly, yeah.
I was thinking how to rephrase my previous question. I guess the question is, how is the semantic token generated? Because I understand with LLM, there's no semantic prediction, right? So the part we're talking about audio prediction, that I got this. But how do you create a semantic model? Because you said it encodes meaning. And how do you get meaning from just audio waves?
Yes, good question. The question was, how do you actually derive the semantics from the audio waves? So I didn't include the part about the audio encoder, or the details about the audio encoders into this presentation. But the model is doing something akin to what BERT does for text. It has a attention layer, or bidirectional attention layer, which is able to attend over the entire sequence of audio, and then come up with contextual representations of each frame with respect to all the other frames. So it's able to capture which frames of audio tend to appear together, kind of like how BERT can capture which sequences of words tend to appear together in order to come up with a vector representation that sort of captures the meaning. And this meaning is not the same meaning that somebody in psychology would assign to meaning. Like Marge would say that it's not actually meaning, but when we say meaning, that's what we're talking about. Yeah.
So it's basically chunking.
Yes.
Can we send that as a space vector that they're giving, and then the distance between all the other ones, that's the median, by the distance that they have, like cosine similarity?
Yes. So for the phone, the cosine similarity between the Uber or wave to vectors represent how similar two audio frames are.
How much bigger space I get because of the numbers?
So I would love to take more questions, but we have more content to get through. So please hold your questions, at least temporarily, so we can get through some more content, because we're already almost at 6:50. So, all right. So modeling raw speech audio is hard. It requires learning both the semantics and the pragmatics of language from audio, which goes into what Sasha's question was about. So for example, learning what words and sentences mean in context, predicting the underlying intent of a speaker, remaining coherent beyond a few words at a time. So we know text LLMs are very good at this, at all of 3 of these things above. But if we condition audio generation on text, then the language modeling problem reduces to an easier translation problem, because we can the model just has to learn to translate text, which is already coherent, into a sequence of audio. And we can see that in Volley. Volley, which came out in 2022, was a decoder-only transformer which predicted it would predict the text trend, I guess the audio verbalization of text that is fed in. So it's a text-to-speech model, except it's able to do it in the style of whatever voice you want. So the prompt would contain text for synthesis, would be converted to phonemes, which would be tokenized and fed in. You'd have an acoustic prompt, which is a 3-second recording of whoever you want to clone, and then it would predict the continuation of the translation of the phonemes in the style of the acoustic prompt. And we can listen to some examples here. So here's some text. They moved thereafter cautiously, etc., etc. Here's the speaker prompt.
He descended the ladder and found himself soon upon firm rock.
So that's the voice we want to clone. And here is the generated text, generated audio.
They moved thereafter cautiously about the hut, groping before and about them to find something to show that Warrington had fulfilled his mission.
Here's another one. Here's a speaker prompt.
Milked cow.
Actually, I want to find one with a different speaker.
Paced up and down.
Maybe a female one.
Windows.
There we go.
The wooden shutters to close over them.
And here is the continuation, the text-to-speech translation.
Yea, his honorable worship is within, but he hath a godly minister or two with him, and likewise a leech.
So, yeah.
They moved thereafter cautiously about the hut, groping before and about them to find something to show that Warrington had fulfilled his mission.
Yea, his honorable worship is within, but he hath a godly minister or two with him, and likewise a leech.
Yeah, those are the baselines. What the baselines are is probably somewhere in the paper. It doesn't say here on the page. So this is generating coherent audio, but it doesn't actually have to understand the language. It just has to copy or translate between the modes of text and audio. So it's an easier problem for the language model to optimize. All right, so now we'll go into some applications and talk about the models that address those applications. So first is speech recognition, text-to-speech, and speech-to-speech. So before we go too far into speech recognition, it's worth a call out to OpenAI's Whisper, which is a very well-known state-of-the-art speech recognition model. Somebody in the audience would say, "Hey, what about Whisper?" if we didn't mention it. But this is not an audio language model. It's actually a text language model that has the ability to attend to an encoder over a log-mel spectrogram, which is a sort of an image-like representation of the audio broken down into its various wave. What's the word? The different frequencies of the wave after it's broken down by a Fourier transform. So this model is not an audio LM, but it is also very powerful, and it's worth mentioning here. Just, if you're looking at the slide deck, hey, what audio models can I use for what task? Definitely consider this one. But now back to audio language models. So we have the speech recognition can be defined as an audio LM as this. So you have some text that you want to, or some audio that you want to transcribe, and the speech tokens are fed into the language model, and then the text transcription would come out. So the language model would have to support both audio tokens and text tokens. Similarly, text-to-speech is the opposite formulation. You have, and we already looked at volley, but this is what it is, it's text-to-speech. We have text in plus an acoustic prompt to condition the voice, and then it will generate the speech codec tokens of the or the vocalized text. And these types of models that take in an acoustic prompt are called voice cloning models, if you've heard that term before, because it can clone somebody's voice. Speech-to-speech is basically takes away the need for a text piece, and you just feed speech tokens in and you get speech tokens out. And optionally, the model could also first generate some intermediate text or semantic tokens that represent the text the speech that you fed in. So there is no text interface on the input or the output, but it could use text internally. So common speech-to-speech tasks include chat, question answering, machine translation, and voice style transfer. And we'll look at a couple recent examples, 2023 and 2024, of these models. So the first is Viola, which is called Viola, the Unified Codec Language Model for Speech Recognition, Synthesis, and Translation. So it's a multitask model that has a single transformer decoder. It also uses an LSTM for some part of the architecture. It uses encodec from Facebook as the codec. It uses the flatten pattern, so it will flatten each time step out into multiple time steps. It uses 8 code books, so each time step is flattened into 8 time steps. There is no demo, unfortunately, for this. They didn't release one. I even found a tweet saying, "If it's so good, where's the demo?" But this is in the literature, so worth mentioning here. They do use intermediate semantic tokens. So first you feed in the audio and acoustic tokens, it will translate that to semantic tokens, then do a continuation in semantic tokens, and then decode it in acoustic tokens. So it's kind of like audio LM, except it doesn't use a 3-stage architecture with 3 different transformers. It sort of pulls that down into 1 transformer. Then there's LoRa GPT. So it's LoRa GPT, listen, attend, understand, and regenerate audio with GPT. They're not talking about chat GPT here. They're talking about the GPT architecture. But yeah, they use transformer decoder. They use a codec called Fun Codec from Alibaba, and this paper is also from Alibaba. They use a vocoder to generate the output audio, as opposed to using a decoder that's part of the codec. And they don't use they don't need to worry about residual vector quantizer handling because they only use 1 code book of the codec. And here is the demo page. So it can do all these tasks. It can do speech recognition, text-to-speech, speech-to-speech translation, speech-to-speech, or speech-to-text translation. It can do speech enhancement. It can do automated captioning. It can do language understanding tasks and also emotion recognition. So there's some demos of each of these tasks. So first is speech recognition. Here's the speech and here's the transcribed texts.
And yesterday, things went on just as usual.
Is it fair that he should do so or not?
So then they waited for a steamboat.
Then it can also work in Chinese.
该歌曲今年一经在各大音乐网站上线，便收获无数好评。
So it's a multilingual model too. Text to speech. So here they have prompt and then a transcription.
Up in the sick room, Zora lay on the little white bed.
So that's the voice prompt, and here is the voice cloning transcription.
At last the cotton combine was to all appearances an assured fact, and he was slated for the Senate.
Here is speech-to-speech translation. So here they don't actually generate any text. It's directly translating the text inside of the latent space of the model.
2 workers in orange vests perform their job.
And now it translates it to Chinese.
2个穿着橙色背心的工人在工作。
2 boys are playing soccer in the water at the beach.
2干来海滩的水里踢足球。
So this is purely, again, the text is just here for us to read. The model doesn't get any text or generate any text. Here you feed in text and you get translated text out. Feed in speech and get translated text out.
但不是这种所有的可能性都可以在市场上成功的。
And the text is, but not all of them can be successful in the market.
Text-to-speech, I think. Did I also see like the stable diffusion type, like the pad, like the
I'm not sure. Yeah.
They actually push the Chinese Chinese act. Like it's a diet. Yeah, like it's really good. I just think the English Chinese one, Chinese tonal voice. There's also the consideration of like accents. Like, I remember showing a Vietnamese global to my family a few months ago. They all kind of didn't like it because it was a North Vietnamese accent. So the pronunciation was very different because they were all South Vietnamese. So that is something. So I guess that's my follow-up question. Are these current state-of-the-art conversations to make that kind of differentiation, or is it just about, or maybe something that sounds convincing if you're not paying too much attention?
I haven't seen any evaluation about tonal languages, but so I'm not sure. But my guess is that the more code books you use, the bigger your model is, and the more data it's been exposed to, it should be able to do it. So moving on to the next one. By the way, it is now 7 o'clock, so anybody who needs to go, thank you for attending until now. If you can stick around, then great. So I'd say we have probably about 15 to 20 minutes left to go. So the next one is Spirit LM. Came out this year, or interleaved spoken and written language models. If you've noticed, if you're looking at the architecture diagrams, each one's a little bit different, but they're all basically the same thing. With some of them have some, enhancements in certain areas, but they're basically all the same thing. We have a transformer decoder. Here, the codec is a Hubert encoder with k-means quantizer. So they're essentially using semantic tokens as their codec, and then they train a hi-fi GAN decoder to decode it. So they don't actually do full end-to-end codec. They do something more closer to what GSLM did in 2021. And it's able to do, it's also able to do multiple tasks. So it can do, it can do continuation of text. So here, the prompt is
A, B, C, D, E.
And the continuation is
6, 7, 8, 9, 10, 11.
Oh, hold on. I did that wrong. The first is a text prompt, 1, 2, 3, 4, 5, and the continuation is
12, 13, 14, 15, 16, 17, 18, 19.
So you can start your prompt in text, and it can just pick it up and continue it in audio. The second example is the same thing. You start your prompt in audio, and it picks it up and continues it into text.
A, B, C, D, E.
And then it continues F, G, H, I, J, K, all the way to the end. And then why don't we go to the beginning and start all over again? Your text prompt is the largest country in the world is?
Russia. Our country has about 150 million inhabitants. The second.
And here is an audio prompt.
Yellowstone National Park is an American national park located in
the northwest corner of Wyoming. So here is a story about a llama that can speak.
This little llama had a friend. His name was Little Dottie, and he could bark. He couldn't speak, but he could bark. This little llama went to school because he wanted to learn.
Yeah. It's a more general model. It's meant to just do general text, interleave text audio continuation. Yes.
Good question. What type of voice are choosing to continue? They look different from all the other ones. How they choose that? Suppose the woman, the other one is a guy, the different guy, and so on.
Oh, the voices?
Yeah, because you're not fitting in the other one, you're fitting the type of voice they should be following. But this one looks like they are following random voice, so they are able to have consistency in the voice.
Yeah, good question. I don't see it in the diagram. The details of that are probably in the paper. Yeah, the question was, how do they pick the voices that they use in the demos? Yeah. There's another version of this called Spirit LM Expressive, which it has to preserve the emotion and the style of the prompt into the audio continuation. So here the prompt is, I am absolutely thrilled to be embarking on this journey, and it's going to be an incredible adventure. And
I'm so excited to have you guys welcome with me this year for 12 weeks, and there's going to be tons of stuff, incredible guests on the show. But I also just wanted to go.
And here, this is unbelievable. My new car ruined. How can someone be so careless and disrespectful? Seriously.
I gotta speak to that guy myself. How come they got my car so much damage? My roommate always says, please have my swipe reader. I don't think she really wants to.
So it can pick up on the expected emotion and tone of the text and then continue it in speech and the other way around.
No, I think you're thinking about Days of Thunder, which is a Tom Cruise racing movie.
Yeah. So that's Spirit LM. I think it's a really cool work. There's also something in the paper that shows that the embedding space between text and audio samples are more aligned when they train it versus if they model text and audio separately. The next one is VoiceCraft. This one is an audio editing model. It just came out a couple of weeks ago. It's out of UT Austin and Rembrandt, which is a private company. This one uses a transformer decoder. It uses encodec using a 4-codebook delay pattern. What this one can do is it's multitask as well, but it has the ability to edit speech. So you feed in an original recording, you basically pick out which part you want to replace with a piece of text, and then it will re-render that text into the recording in the original style of the recording. So here is the original recording.
Fast cars, that had the nice clothes, that had the money. They was criminals.
And now here is the edited version where they insert the words that had expensive gold watches.
Fast cars, that had the nice clothes, that had expensive gold watches, that had the money. They was criminals.
That's really good. And you can take a politician and basically make them say whatever they want within their original speech with this technology. So pretty scary.
We would just be open and willing to adopt whatever child God brought to our life.
And here they insert the words excited to welcome.
We would just be excited to welcome whatever child God brought into our life.
So if you think about it, text to speech is a specialized version of this general audio editing problem where there is no existing text that there is no existing speech that you want to edit. It just needs to generate all of the text that you enter. So they can do zero-shot text to speech, and they compare themselves with Volley, which we looked at before. So here is a 3-second voice prompt.
Like there's this one sketch we did that was about the
and
that would appear whenever racist stuff.
So the first 3 seconds are used as the prompt, and the transcript is going to say this text over here.
I don't want to make it as a thing where I'm absolving myself of any responsibility.
So it didn't edit the voice because there was no voice. It just generated it. And they compare it to other baselines like Volley.
I don't want to make it as a thing where I'm absolving myself of any responsibility.
No, it's close, but this one is, I guess, a little bit better over the course of some evaluation metrics that they use. So VoiceCraft is a pretty new model. It's open source. It's very powerful. Definitely recommend checking it out if you're interested. Finally, we have natural language guidance with high fidelity text to speech with synthetic. I think I missed some text there. I'm not going to go to the demos for the sake of time, but check them out. There's an open source reproduction of this called Parler TTS on Hugging Face, which you can use. And they use the DAC codec, the discrete audio codec. They use the delay pattern with 9 codebooks and a transformer-only architecture. What's special about this model is that you can actually use a text description to condition properties of the voice. Rather than a voice cloning, you can just say, I want a, I'll play one demo just to show you. So you can say something like, a female voice with an Italian accent reads from a book. The recording is very noisy. The speaker reads fairly quickly with a slightly high-pitched monotone voice.
Here and there around her the leaves on the ground trembled luminous patches.
So that noise in the background was conjured up by the prompt. Yeah. Here's some more links to other stuff which we didn't have the time to cover. Finally, not finally, but I guess next we have audio and sound effect and music generation. So here, it's a similar task to speech to speech, except here we're not translating from text into or semantic tokens into speech. The text just serves as loose guidance. So this is more like Stable Diffusion or Midjourney for generating images. The text prompt is just there to guide it, and it does the rest. So you feed in the text guidance prompt, an optional acoustic prompt if you want to do some style transfer or set the style of the text of the generated sound effect, and then the audio codecs will be continued into either music or sound effects. So the first model that does this is AudioGen. Similar architecture, 4 codebooks in a parallel pattern, transformer decoder, and here are some samples. So here the text, the prompt says, a man speaks as birds chirp and dogs bark. Whistling with wind blowing. Sirens and a humming engine approach and pass. So it's the same exact framework as we've been looking at this whole time, just for different inputs, different outputs. Then we have Music Gen. Music Gen, if you remember this image from the earlier in the presentation, this was the only figure in the paper, but they formalized the delay pattern and they use the delay pattern for music generation. The examples are pretty good. So the prompt says what type of music you want and it will generate it. So a grand orchestral arrangement with thunderous percussion, epic brass fanfares, soaring strings, creating a cinematic atmosphere fit for a heroic battle. Drum and bass beat with intense percussions. Rock with saturated guitars, heavy bass line, and crazy drum break. Yes. There's also Suno AI's Chirp product, which is not open source, but it gives you a more end-to-end generation capability. So you just prompt it with what you want the song to be about. It'll generate lyrics, it'll do the music generation, vocal generation using some type of styled text-to-speech and put it all together. And it might be in codec based if they followed their earlier Bark product, which is an open source text-to-speech engine. So just some example. So here you type in the prompt, what you want the song to be about, and it will generate everything. So here the prompt was an indie pop, soulful, dreamy, psychedelic song. So it generates these lyrics and it puts it together. Oh, I guess I have to hit here.
Oh, my love, my friend, you know, it's been a while without thinking of you, but the thought makes me smile.
So this was 100% AI generated, all from a prompt.
There's no that on Apple Music.
Because I got a hit on Shazam.
Yeah,
Yeah. That song has 248 Shazams.
they
But it's called Stone. Yeah.
they put it up, they uploaded it there, I guess.
Yeah, probably. I just wanted to-
There's another one called "Lying on the Railway."
Lying on the railway beneath the spooky night, moonlight casts its shadows in the pale moonlight.
And here's one in German just for Sasha.
Viele Jahre fahr ich schon, an dich schon lang mein Herz verloren. Der Wind die Haut zu Leder wäscht, wenn Sturm und Regen auf mich wäscht. Die Burg im Norden war.
How good was that German? Yeah. Legit. Okay.
Yes, actually, so let me just finish off the last piece of the presentation, and then we'll open it up to questions. So it's already 7:14.
Yeah, I want you to do like your favorite thing from these full duplex technology.
Yeah.
If you have the links to these demos in the presentation and the slides, I'll be able to share them.
Yeah.
Yeah, so the slides will be shared.
Yeah. So then, I'll go through this really quickly. Basically, we know that speech communication is richer than text because we have things like pauses, fillers, laughter, back channel communications like right? And you can represent these in text using special annotation schemes such as ChatCA, but ideally we want dialogue agents that can replicate all of that. So if you stick a text LLM in one of these things, you can get a speech-to-speech dialogue agent, but ultimately it's just going to be a cascaded model which loses context of the original speech by the time it's generating a response. They fail to produce fluid, lifelike interaction because they are rigid, half duplex, fixed turn taking, and they have no modeling of prosodic and paralinguistic features. So natural human conversations have lots of different phenomena in them. I'm not going to go through this whole list, but turn taking, choral speech, speaking in chorus, laughter, prosodic cues, etc. And cascaded dialogue systems do pretty much none of these well. So you can compare ChatGPT voice chat to a real phone call to see what we mean here.
Shop Springfest deals from top paint brands, now at Lowe's.
Thank you, YouTube.
Take an extra 30%
Thank you
off
again, YouTube.
designer brands that rarely go on sale today at Macy's Friends and Family.
I just got access to ChatGPT voice conversations, so let's chat with her. Hey, what's up?
Ago, so
Can you hear me?
Hey, I can definitely hear you. What can I do for you today?
I was wondering, what is your name?
I'm called Assistant. Nice to meet you. What's your name?
My name is Andy. Are you better than the other assistants like Google Assistant or Alexa?
I like to think I have my own unique strengths. I can understand and generate human-like text pretty well. It really depends on what you're looking for in an assistant.
Yeah. Now compare that to a real human phone call. I don't know why I have to log in here. This login was not here as of like a week ago, but everybody's got to protect their stuff, right? Not authorized to view the transcript. Wow. Okay, we'll pick a different one. So here's a real human phone call.
Did you get that? Okay. We're making $20 on it, and we get a free 30-minute phone call, and we make $20.
Wow. How do you sign up for this?
Actually, I'll give you the phone number. And actually, you get one for international calls too, where you can talk 30 minutes anywhere in the world, and you make $20. And it's a free phone call too.
Wow.
So we get all these cool.
Well, you're getting smart in this.
Hey, we're just, we're looking inside.
I don't know if we can actually hear the other person. It's very low.
What do you think?
Publicly distributed, Jim.
Oh, don't. I wouldn't sweat it.
Yeah. So the human conversations are much more fluid. They have a lot of overlap. So yeah, I'm going to skip some of this. Basically, there are issues with doing this with the cascaded models, but this has been attempted to be done using neural models, such as Google's Google I/O demo 2018.
We think AI can help with this problem. So let's go back to this example. Let's say you want to ask Google to make you a haircut appointment on Tuesday between 10 and noon. What happens is the Google Assistant makes the call seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
Oh, how can I help you? Hi, I'm calling to book a woman's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m.
Yeah. So this was done in 2018, and they didn't publish a paper, but since it was 2018, based on the state of the field, we assume this was a very specialized and domain restricted model that wouldn't be able to work for any general conversation. But that's what we want to do. We want a general full duplex dialogue system. And so why not use a speech-to-speech audio language model for that? And this paper called DGSLM attempts this. So this is the DGSLM demo page. Similar to the other audio language models, there's a prompt and then a continuation. Here's the prompt.
Hi, my name is Dee. How are you? What's your name?
Oh, I think one of our audio channels is not working. No, I think it's the speakers in the room. Yeah, it's one. Yeah, it's stereo speakers, but one of them is not on. But anyway, here's the continuation.
Hi, my name is Dee. How are you? What's your name?
My name is Debbie.
Debbie. Where are you calling from?
North Carolina, and it's vaccine age before or right up. Yeah, people on habitually care stand up.
Oh, gosh, wow.
Yeah, but she has at least big town here from the theater one by was. You can't imagine.
Oh, I see.
I don't know why we can't hear the other speaker. I think there's definitely had like some issue in the room. I don't know. People on the WebEx can probably hear it, yeah. But anyway, you can notice if you listen to these that they sound natural, but they're not actually coherent. They don't actually sound like any real words. The model is able to capture the dynamics of conversational coordination, but it's not able to actually understand language. And this is because unlike the other speech-to-speech models we looked at, there's no intermediate text or semantic tokens to reduce the audio language model problem to translation. So it's a harder problem. This is the architecture of GSLM. It's basically the same as AudioGen, except they use a dual tower LLM to model each channel simultaneously. So you can see there's speaker A on the left, speaker B on the right. They're both going through the audio LM at the same time, and there's a cross attention between them. So, yeah, so that's pretty much it. So what's next, right? How can we solve the coherence issue for a full duplex audio model? Just scale it up and train it on more data maybe, or align its embedding space of text LMs that are already very coherent, or use intermediate text and semantic tokens. And this is actually the topic of my PhD thesis. So if you're interested in this, come and talk to me. You'll have a hard time getting me to shut up about it. So that's it. Thank you for sticking through. Here are links to a lot of these models on Hugging Face. There are some that aren't on Hugging Face, but they have GitHub PyTorch implementation. So if you want to get your hands dirty, use the links in the slide deck, and you'll be able to find your way pretty quickly. That's it. Right now, any questions? Yes, go ahead.
What is that one are these semantic tokens connected together at the same time? And two, how do you determine the width of the how do you determine like is the length of is the less fixed or is it lower?
So the question is, are the semantic and acoustic tokens, I'm guessing you're talking about audio LM, and the other one that used it was Laura GPT, I think? If I remember correctly. How do those train the acoustic and semantic tokens? Are they jointly trained or are they trained separately? And is the length of them fixed or learned? So they're trained separately and the length is fixed. They're trained separately because the semantic tokens are usually based on bidirectional encoders such as Hubert or wave to vecbert or wave to vec. And the acoustic tokens are based on codecs like encoder, soundstream, or discrete audio codec. So it's separate models, usually separate data sets, and that's sort of the way it is. But it would be interesting if somebody is able to do a joint modeling. That would be novel.
They're able to work together well, even though.
Yeah, because it's essentially the language model treats it as just two different languages, and we know that multilingual LLMs work well. So, well, Elkin had a question, but oh, let's see. See if I can open the chat. Oh, here it is.
Ask in the chat or just?
Oh, there is nothing in the chat.
Yeah, but you raised his hand. You just maybe ask it. It's for fun.
Oh, I think you have to unmute him.
Oh.
Okay, go ahead.
Do I get to ask?
Yeah.
Oh, sorry. Okay. I have a few questions. Great talk. Can you go back to the slides on codecs?
Yes, 1 second. Was it
with the one with the Voronoi diagram where it shows the codebooks and the embedding lookups?
Oh, yes.
The very beginning. Yeah, thank you. So the codecs are it's basically like a compression problem where you have the audio and you'd want to convert it to a discrete representation that you can reconstruct, right? So it doesn't necessarily capture the semantic meaning. Whereas in audio LM, they do have semantic tokens that are learned. So the semanticness or what the semantic tokens that are later in audio LM are basically learned representations of the codebooks or the code word indices themselves, right? Where you're looking at which code word indices co-occur together. That's how it learns the representation for each code word. Is that correct?
If you're asking how does the language model learn to understand the semantic tokens, then the answer would be yes. If you're asking how are the semantic tokens actually trained in the first place, it's a different process.
No, it's just how they're understood. Just the gist of it.
Yeah, so they basically they'll start with a randomized embedding matrix, and they'll learn new embeddings in the language model to represent the code word indices from the semantic codebooks.
Got it. Okay. Another thing is, given your understanding of the literature so far, because there are multiple code books for each or there are multiple you mentioned there are 32 code books for each codec. Is that correct, or something like that?
Each codec has a different number of code books. So and codec goes up to 32 code books, but in practice, most models will only use the first 8.
Got it. And the more code books that are used, the better the performance because there's more information.
The better the better the reconstruction performance from the codec decoder. But if in terms of the language model, it's the other way. As the fewer codec codes that you use, the simpler the language modeling problem. So it'll converge faster and get better performance.
Makes sense. What are your thoughts in general about like multiple modalities? Like if this is to include video as well, you even have even more signals. What are the most, do you think that codecs would be one of the most crucial pain points of multimodal AI systems that are holding, that everything depends on?
I think absolutely. So right now, models that deal with video, and I'm excluding models like Sora, which use diffusion to do generating video. Autoregressive models that take video in are generally text-only output. So they'll take a video in and they'll do like question answering over the video. The video ChatGPT was one of those. Video Llama was another one. But those don't use a codec. What those do is they directly project the embeddings from the encoder into the vocabulary of the codecs, the vocabulary of the language model's embedding layer. And then they don't have to worry about generating it, so they don't need a codec. But once we have models that can generate and input in video, and like interleaved audio and imagery, then the codec is going to be critical because that's going to basically determine what the sequence lengths are and the quality of the reconstruction.
Got it. Makes sense. Assuming that we have a language model that can attend over infinite length, would that also would that alleviate the need for more compressed codecs, or not necessarily?
If the language model is able to really attend over infinite lengths with no performance degradation, then yes. But I think that even language models that claim to support really long contexts will ultimately suffer from the same issue that that the shorter ones do, which is that if the data is too sparsely represented, then it's going to have trouble maintaining coherence. A lot of these really long context language models are using some kind of sliding window attention. So ultimately, you go past the sliding window, and so if you had a theoretical language model that doesn't use a sliding window and can really take in all of its context and attend to it perfectly, then sure. But that's not realistic.
Okay, I think we'll,
thank you.
Let's call it there. It's 7:30. We're gonna call up there for questions and give Abraham a break. Let him finally eat some pizza if he still wants to. This recording will be posted, and Abraham's slides will be posted in the next few days. So let's give Abraham another round of applause. That was a great talk. Thank you.
Bye, everyone.
Thank you so much for the talk.
Attending.